All right, let's get started. So we have a real banger today. This is one of the extensions of the core general linear model. So we're going to spend most of class talking about an extension of what we did in class last time. So we're going to look at census records and run some statistical models. And we're going to test for the presence of a gender wage gap in the census records. And we're going to do this in 3 different ways. Using increasingly complicated versions of the general linear model. So we're going to test a couple of different types of presence of the gender wage gap in different types of settings. So I'm pretty excited about this one. Before we jump into the work for today, I wanted to walk through a couple of things related to the final project and homework 10. I'm going to give you checkpoints as we work our way towards the final project, and they're going to often be embedded in the homework. So this is the first homework where we're actually making some progress towards the final project. So I just wanted to talk through this. It's going to look a little different than the homework you've seen before. So what's up? You like the homework?
I just thought it was fun.
Yeah, cool. I find the homework funny too. So the first question is that you're going to formulate your own question. The question you're going to put into the homework doesn't have to be the same question as what's on the final project. This is not a commitment to a research question, but I just want you to be thinking about the project itself. So you'll just set up a question and put that in. Also, the final project is a lot of work. Like, you're not going to be able to do it in 2 days right before the final project is due. So, and because it's a lot of work, I also recommend working with someone else to share the workload. You all have worked in groups on group projects before, and often I can imagine they haven't gone well. So what I recommend for this final project is not to find a couple of people to work with, but if you have someone else that you're interested in working with, like one other person, like a friend or someone you know who you think might be good to partner with on the project, this is the place to put their name in. So I'm forming groups at the moment. So the second question is basically to find someone who you're interested in working with. So you'll put in the name if you know who it is. But for a lot of people, like you may want to work with someone you don't know who you want to work with. And maybe you want me to find someone to work with for you. So if you have someone, that's great. If you don't have someone, but you know you want to work with someone, put in that you would like to work in a group with someone, but you don't know who it is. And I'm going to do a little back-end work looking at the research topics you submit, and then try to form groups based on research interests. I wouldn't recommend working alone, but you're more than welcome to if that's your choice. So the third option is to work by yourself. And then the third question is about essentially getting started with a data set that's relevant to your question. So you're going to go through the internet and try to find a data source that can get you in the ballpark of thinking through your question. And a couple of things I need 2 variables. So whatever data set you work with, I need at least 2 columns. These could be continuous variables or discrete or categorical, whatever the case may be. I just need 2 variables. And then I also need that there's a sufficiently large number of observations. So usually this is like greater than 30. It doesn't have to be 30 as a cutoff, but just make sure that you're dealing with enough observations. And then you'll just give me a link to where you got your data from. I've also given you some extra resources here for final projects. So I mentioned this at the beginning of class, but you can find the guidelines for the project here. You can also find some project proposal ideas. These are just some quick ones I wrote up like last fall. So if you want some extra guidance in getting started with a research question, you can use these. If you use one of these ideas, I recommend changing it slightly so that it matches your interests more directly. The main point of this final project is for you to demonstrate the full pipeline, all of the skills we're developing in this class, on something that you're very interested in, or medium interested in at least. So take a look at this. You can see some interesting research ideas. I've also included a long list of the projects that my past students have worked on. So you'll see data sources, methods, and research questions. So this is at least a place to start and think about what you might be interested in working in. A good place to brainstorm. And then I've also just included a summary of the questions, the data sources, and the methods and the findings for a few projects from last semester. So I think this is really cool. I love highlighting student work, especially when it looks this good. So take a look at that. So that's a place to get started with the data. And then for question 4, I want you to actually use the data to create a visualization summarizing your data. So particularly as relevant to your question in question 1. And then you're just going to interpret the visualization and then use some version of the general linear model to make a test, run a test on your data. So this can be something really basic. It doesn't have to be sophisticated. In fact, at this stage of research, it really, truly does not need to be sophisticated. But I just want you to get started running models on your data. So this may look like a lot. It may look like something you could do in 15 minutes. Whatever the case may be, this is we're starting to get started with our final project now, making progress towards something that's presentable at the end of the semester. So feel free to stop in for office hours on Thursday for this stuff. But I just wanted to talk this through just to give you a heads up. It's due on Sunday, so you have the whole weekend if you like, but definitely get started on this early. Okay, any questions here? Yeah, Ben.
Can you do multiple data sets?
Yeah, so you can merge data sets together, yep. Or you could do 2 different questions if you like, but all you need to do is submit one here. Yeah. What other questions do we have? All right. Anyone want to know about the gender wage gap in the census records? So I talked to you last time about returns to education. So this was in part 4.4. So we walked through this last time, and you found in this notebook we have, so we loaded this this data set just straight from can't type apparently. Just straight from iPooms. So some of you are actually going to work with this data set or some variation on this data set, but you can go through and select different years. So we have data that goes way, way back. You can play around with this. And there's lots of information here. So we have lots of demographic information. There's some geographic information too. So lots of information here. This is all from the census. So what I did is I just downloaded a data set for education and income. And what we did last time is we actually just ran through this data set and plotted summaries of the different variables we were interested in. So this was education, different years. We had income total. We found that this was very skewed. So it was zero inflated, lots of pressure towards zero. Then we talked about education and income. We walked through these models, and we built regression models trying to answer the question, is education associated with higher incomes? And if there's an association there, what's the strength of that association? And so what we did is we built a model trying to predict income using education. And what we found is that there was a positive relationship between education and income, as you probably expect. This is great news if you're in this room. This doesn't give us a causal relationship, but it does tell us that the more education you have, the higher your income tends to be. But then we walked through and we plotted out the residuals. So this gave us a picture into the assumptions for the validity of our regression model. And so what we did is we plotted a residual. We saw that it was not normally distributed, but because we have very large sample, we're able to still be comfortable with this distribution of residuals. Then we talked about the residual plot, which is on one axis we have the prediction of the model, and then on the other axis we have the actual residual itself. And we see increasing error as income goes up. And so this was a problem. Someone remind me what this problem is. That's correct, I think. Or maybe my hearing is failing me. Someone help me out. What's this problem? Yeah, Luke. Fails homoscedasticity. We don't have a consistent distribution of error terms. We have increasing variability in the error term. So variability for high income is much higher than it is for low income. And we talked about why that might be. So this is a problem. We don't want to run a model that looks like this. We can fix this problem in two ways. One, we could run heteroscedastic robust standard errors. And we talked about how we might do that in code. It's pretty simple. This is one of those cases where I gave you a method for solving a problem without telling you how the method actually solves the problem. I hate doing that. No intuition for why this works. But we can adjust the standard errors to account for heteroscedasticity just by using robust standard errors. But another approach is to transform the dependent variable. So we talked about log income. So what we did is we took the income and we took the log of it. So on the horizontal axis, we just have the log income. So when we go from log 10 income, so that when we go from 3 to 4, we're increasing by a factor of 10. So one increment on the horizontal axis, because it's a log 10, is 10 times larger. So if your income is 3, log income is 3. That's 1/10 log income at 4. And 4 is 1/10 log income at 5, and so on. So it's a little bit harder to read what's going on, but it allows the y variable to be normally distributed. And so we ran this model, and it turned out we had roughly a 10% increase in income associated with every additional year of education in our data set, which is a pretty big relationship with education. Okay, and then we went through and checked the specification of this model. So this was, the residual plot. This is like the most boring thing for me to say. we're checking the residual plot. It sounds like super boring and like in the weeds, but this is how we check whether the model is working for us. All right, and then we checked the distribution, and this is like exactly what we want to see. Like no relationship with the error terms, just a nice scatter plot. And then so we walked through and talked about control variables. We included age and just age in our regression. And we left with this final question, which was, which one of these two models is better? The one where we control for age, or the one where we don't control for age? The predictions are very similar, but they're slightly different. Do you all remember the conclusion here? It's like the last 3 minutes of class, everyone's brain is out the door. But this was one of those big ideas, which we will return to. Do you remember which one of these was the better prediction? Controlling for age or not controlling for age? Well, in this case, I would say controlling for age is the better model. We're saying holding age constant, so we compare two people with the same age but different education. We have higher income with the person with higher education. Education is associated with higher income, even after we control for the possibility of age impacting your income. So I would say this is the better model. But we definitely don't know whether there are other factors that are impacting income and impacting education. If you're in this room, I imagine you're more motivated than average, just like generally. And motivation, we know, impacts your income. If you're more motivated, you're more likely to have a higher income. So motivation, which is something that we don't measure, can impact both your education and your income. And if we could control for that, that might give us a better perspective into the relationship between education and income. But we don't have it measured. If we included it in our model, that would change the coefficient. So the better, the more things we include in our regression, the more we change the estimate of the regression model. But so many things we just can't measure. So we are omitting those variables, which would have an impact on our regression model. This is what we call omitted variable bias. When we start talking about models of causality next week, we're going to talk more about omitted variable bias, things that may impact the model, but we just can't see them. There are lots of those things going on here. Okay, so this is what we did last class. Today, what we're doing is looking at a slightly different regression model. So instead of simply looking at the returns to education, what we're going to do is test for differences by gender. So what we call the gender wage gap. And we're going to have to do an approximation with our census records because we don't observe, the census doesn't measure gender, they measure sex. These are the main questions for today. We're going to try to address the gender wage gap using a general linear model and census records. Here are some of our questions. Is there actually a gap? And then, is there even a gap in the returns to education? Which, to me, doing the job I do is of particular interest. Something we're very concerned about. And then how do we set this up with the regression general linear model framework? So this is where we're going. And we're going to do this basically step by step. So before we get into actually building this, I just want to show you a picture of the data. So this is, we've sort of talked through most of this already, but we have this sex variable, which is coded in the census record as binary. One of the issues, like the coding issues with it. We have our age variable, which we controlled for last time. We have this, I constructed this edu variable, which is like how many years of education you have. So 12 is a high school diploma, and then 16 would be a bachelor's degree. And then what I've done here is, because we don't have gender recorded, we're going to use sex as an approximation. So what I've done here is just constructed a binary indicator variable using the data we have. So if it's 1, then you're male, coded in this column, and if you're 0, then you're not male. Which we're going to call female. So this is what we have to use the data that's available to us and be very clear on how we're constructing the variables that we are. Okay, so this is the data we're using. And this is, so the pictures in the slides are going to be with synthetic data, but we're actually going to use the real data in the notebook. So this is a picture of wages. So we've broken the data into 2 groups, male and female, and we're going to check wages on the vertical axis. So if you were interested in testing whether there were differences in income by gender, how might you do it? Everyone's like diverting their eyes when I look at them. Yeah, Luke.
Take the difference between the 2 averages, between the 2 categories.
Okay, so perform like a 2-sample t-test where we take the difference and then construct the standard error of the difference and then use that. Yeah, so 2-sample t-test would work here. If we were to write out a 2-sample t-test using a general linear model, how might we do that? What would that model look like? Bless you. What about this? So if I'm going to write a general linear model 2-sample t-test, what I want are 2 lines running through my data. I want the mean represented for both of the two categories. So here I have the average for the green group, and then the average for the red group. And then here we have the base wage, which is the average for the group that's coded as 0. And then what we want is to find this additional sort of difference on top of the base wage, which is our gender wage gap. So I'm just going to write out the equation. It looks like this. We have wage, so we're trying to predict wage using both an intercept term and a binary indicator variable for one of the 2 categories. And I'm going to write this out using the male column, but we could equivalently use the female column. So we could just construct female, which would be just this. So here we have both a female and a male column. And unfortunately, this is coded as binary in the census record, so this is what we're left with. This is our t-test, and this gives us the ability to answer the gender wage gap using the census records. So someone tell me, what's our null hypothesis here? We have a two-sample t-test, but in the context of the general linear model, what is our null hypothesis? Luke?
It would be no difference.
No difference, yeah. Someone restate Luke's null hypothesis of no difference in general linear model terminology. Like, what is it that we're testing for? Yeah, Garen.
E1 does not equal 0.
So beta 1 relative to 0. I'm going to make the claim, I'm going to say it's the converse of what you said.
Well,
So
we know about, B1 equals 0. We're testing to see if B1 does not equal 0.
very nice. Yep. So beta 1 is equal to 0 is our null hypothesis. So we're going to go into this trying to check whether beta 1 is equal to 0. All right. So I recommend you follow along in your notebook if you have it, because we're actually going to run 4 different models and check 4 different kinds of things. So the first one is this two-sample t-test. We're going to include what we call a fixed effect, which is just a coefficient on a binary indicator variable. We've talked a bit about this, but we're going to run this as a two-sample t-test like this. All right. And so someone interpret what we're seeing here. Someone interpret this line in the context of our null hypothesis and our question at hand. So what I've done is I've tried to predict income using a vertical intercept and a binary indicator variable for male. Leaving me on red again. This is like one of the core skills. Yeah, Garrett.
Would it be that men, the difference between the female wages and male wages is like about a 50% increase, or like a slope of 1.5. Your P score kind of confirms that. It's a very low P rating, which means it's probably statistically significant.
Yeah, so the probability of seeing something this extreme due to random chance under the null hypothesis is basically 0. And the interpretation here, because we're using log scale, so log income, is actually pretty difficult. But essentially this is like 15%, like roughly 15% difference in wages, which is incredibly significant. This is something we need to be thinking about as a society. Actually, how many of you are part of the economics undergraduate hub on Canvas? Okay, so you probably got an announcement recently that Lisa Vesterland is talking to one of the student groups on this topic, the gender wage gap. She does a lot of research on the gender wage gap and is speaking to, I think the club is Women in Economics. So if you get that announcement and you're interested, she's talking about this stuff. I think it's April 1st. Okay, so great. So this is the result of our model. Any questions here? Two-sample t-test. We're just checking for differences between the two groups. And the way we interpret this, beta 0 is just the average wage for anyone coded as 0 in the data, which in this case is female. beta 1 represents the difference, sort of the additional wage associated with being coded as 1 in the data. But the problem here is we just gone through this whole thing talking about the returns to education. And what we've done by just looking at the actual difference between the two groups is ignore all the possibility of differences in education leading to this result. So what we're going to do next is actually control for education. But I want to show you another thing before we do that. So we constructed this female variable. So everything we can do here, we can do using female as, so it doesn't matter which binary indicator variable we're looking at. But you can see if it's male, we say there's like a 15% or 16% increase in wages associated with being coded as male. And if instead we were to do this with a female indicator variable, it would be a negative 16%. So it's the same number, it's just the signs are different depending on which way we're coding it. So if that's nice, that's nice. And if it's complicated for you, then just think about the one way of coding it. But the choice of how we code it doesn't matter. Okay, and here's the code if you want to run it. Just for code here, I have the notebook posted, the data posted, and then the slides. So you can just use my code, or you can use the code from the slides. Okay, so we've used the tools we've developed in this class to actually say something pretty conclusive about the presence of the gender wage gap in the census records. Remember, this is not synthetic data. This is coming directly from government records on wages and our population statistics. Okay, so like I mentioned, this doesn't control for things that may impact wages. So what we're going to do next is actually include the presence of a return to education. So here I've coded two groups. So one is in red and one is in green. If we were trying to test the presence of gender wage gap while controlling for returns to education, so on the horizontal axis, this is years of education, how might we do this? When you see data like this, the thing I want you to do first is to try to draw some lines. So how might we draw lines that allow us to test the presence of a difference in the intercept? Like just scaling up and down. I want you to actually think about this. You're going to do something like this in your final project. Lots of projects will require this kind of thinking. Before we start writing down a model, actually, can I have you chat with someone next to you? Is this annoying? Just say something nice to someone next to you, and then maybe suggest how to resolve this question with data. Nope.
Oh, really?
Just one test.
Just one test.
Okay.
Is one of them education? Is one of them accounting for education? One of them is not.
Okay.
Gotcha. That makes sense.
Okay. So if you were to just draw some lines here, you want to check whether the vertical intercept is different, but you also want there to be a slope. Someone tell me like a general approach here that might work. Not thinking about regression equations, just thinking about lines. Okay, so we're going to draw two lines, one for both of the groups. So we'll draw a green line through the green data and a red line through the red data. And then we're just going to check whether the vertical intercepts are different. Any questions here? So I'm going to draw a picture, and I'm going to see how many of you drew a picture in your brain that looks similar to this. Raise your hand if you had in mind something along these lines. And raise your hand if you did not. No one. Okay, so everyone else abstains. Respect. So this is how we can test the presence of the gender wage gap while controlling for a variable like education. So we're going to have the possibility of a gender wage gap while still being able to account for the possibility of education impacting the thing that we're trying to find a gap in. So the vertical axis. So if someone were to write down a regression model to match this picture, actually, let's take maybe 30 seconds here. Say something, give the person next to you a compliment, and then tell them what you think the regression equation might look like. Okay, someone give me an incorrect answer. Or you can maybe try to give a correct answer if you like. But someone give me something wrong. Wrong answers only. I know you have wrong answers. That's what we're doing today. Wrong answers. What's the y variable? Ben. Wage. Wage, or log income as we have in our data, is our y variable. And then we have base wage, which is our beta 0. So it's just the vertical intercept when you're coded as 0. What else might we have? What's another variable we could include? Luke. Okay, so which coefficients would we use?
So those are the y coefficients or the initial coefficients.
Okay.
And the slope coefficients as well.
Okay, so we'll include our x variable in this case is going to be education. And we'll have some beta on that. And then Luke is also saying we're going to have beta 2, which is on our male code. So the 0-1 male variable, our binary indicator variable. So maybe something like this. Did anyone write this down? So we have wage as our y variable. We have beta 0 as the base wage, so everyone coded as 0. We have beta 1 multiplied by education. So this on its own is the model we ran last time. Just an intercept, a slope coefficient on education. But then in addition to that, we're including this. So it's beta 2 times male. Or we could write this as beta 2 times female if we wanted to. And this beta 2 is going to give us the difference between those coded as 0 and those coded as 1. Just on the vertical axis. So that beta 2 is the gender wage gap controlling for education. What we've done here is assume that the slope on education for both groups is the same. Okay, any questions? Lots of questions. So let's interpret these things, and then we're actually going to run this. So beta 0 is the base wage for those with no middle school education. So you're coded 0, and you have 0 education. Beta 2 is the gender wage gap. And then beta 1 is the slope for education. And we're assuming parallel lines. So this is the code. And we're just going to plug this in, and we're going to actually run this. So this is our model 2. So we have log income, we have education, so we need that. And then we're going to have this 0, 1 binary indicator variable, which gives us different intercept terms for the two different groups. And we're going to run this. And then you're going to interpret this for someone sitting next to you who has just complimented you on something. Okay, so compliment, how about this? Give yourself a compliment, but say it to someone next to you. And then once you've done that, then interpret what this is telling us. Is there an observed presence of a gender wage gap after we control for education? We'll take about a minute here. Yes, you have to compliment yourself. Okay. Someone tell me how to interpret this regression output. What is this telling us? Is there evidence of the gender wage gap after we control for the returns to education? I'm going to compliment Luke. Luke is amazing at showing up every class and giving me answers to my questions, but I'm looking for someone else. Yeah, I'm sorry. You're going to have to remind me of your name.
Dylan.
Dylan, that's right, yeah.
So I would say being male has a significant increase compared to educational load and increasing your wage.
Okay.
Based on like since the p-value is less than 0.15.
Nice. So we have a very small p-value. So this bump in income is very unlikely to be due to chance alone. It's sort of difficult for us to compare these two things, these the coefficients on male and on education, because education is a sort of a continuous variable. So it's giving us the slope where male is a binary indicator variable. So I probably wouldn't compare those two things, but the number for male is large. And we could run this too with female, and we'd see the same result, just with the opposite sign. So we're saying if we treat male as the baseline instead of female, then we get a negative difference. Okay, so either way we do it, we get p-values that are very significant. So this is not going to be due to chance, even after controlling for the returns to education. A little disheartening. Any questions here? All right, so this is our model of the gender wage gap after controlling for education. But we might also be interested in another question. One question I have as an educator is, are there differences in returns to education by gender? So is the gender wage gap not just in baseline, but are there different slopes? So I'm going to show you another picture, and you're going to try to construct a similar kind of model using the general linear model, but for different slopes, so different returns to education by group. So if you see this picture, how might we, before we think about writing any regression models, let's just try to write down like a regression line or multiple regression lines that allow us to have different slopes. And maybe to make things a little bit simpler, let's not allow for differences in the vertical intercept. Let's make one vertical intercept for both groups, but allow for different slopes. So I want you to draw a picture. Actually, the first thing we're going to do is you're going to offer a self-critique of yourself to someone next to you. And then you're going to talk about how we might draw a picture. So give yourself a little bit of like constructive feedback, and then we'll draw a picture. Take about a minute here. Only constructive feedback. You're doing great. Okay, someone help me out here. What's the picture we would draw? So, try to characterize it in words. No difference in intercept, just difference in slope. Tough crowd today. Nice. Front row, all three. So Luke always answers. Dylan just answered, so maybe Ben.
Would it be the same as before, it was just the two positive lines?
Okay, so two lines and both running through the same intercept. And then we're just going to allow two slopes. So maybe this is sort of a simpler question. Okay, how many of you did this or thought about doing this? Okay, self-critique. Maybe I could elicit your feedback more often. Okay, so this is what we're going to try to build a regression model for. We have two slopes, and we're going to try to test if they're different. So our null hypothesis is going to be that these two slopes, these two lines, have different slopes. This is, again, synthetic data, so this is not like a real picture. This is just what I would hypothesize. Our null hypothesis will be that these two are different. So someone translate this into a regression model if you can. So our y variable is our vertical axis, so it's income or wages. And then we have a beta 0. But then what else are we doing to get this? Like, I'm going to show you a regression equation in a second. What's that equation going to look like? Luke. Was your hand up?
I'm still thinking.
Okay. So we know there's going to be a beta 0, which is going to be the vertical intercept. Dylan.
Would it be B0 plus B1 times, would it be like female, wait, is it be a male, female, would that be there? Or is it?
Could be.
Okay, and then plus B1 plus the quantity B1 plus B2 times like the male factor, and then plus like the E.
Plus epsilon.
Yeah.
I think it's going to be slightly different than what you said, but there's some good ideas. So what Dylan's pointing out is maybe we actually have like we're sort of combining coefficients to give us like we're estimating two coefficients at once, which is sort of in the right direction. It's not exactly what we're going to do because we can't actually do that with the general linear model, but it'll be something like that. Luke. Okay, yeah, so maybe not that. Wrong answers are encouraged. Yeah, Dom.
Maybe B0 plus B1 times education plus B1 plus B2 times the difference between male and female.
It'll be sort of, I think that's pretty similar to what Dylan was saying. So it'll be pretty similar to that. But it's not going to be exactly that. Let me write this up, and then we'll talk about what it means. And I'm going to show you an example. So we're going to have beta 0, as always. Just going to be the baseline income for everyone coded in the data. So here we're not including different intercept terms by group. We're just including one intercept term. Because on its own, there's no additional binary indicator variable on its own. But then we also have beta 1 times education. We are almost out of time. Let's get through this. And then I'm going to show you one more model, and then I'll let you go. We have beta 1 times education. So this is our baseline slope. But then I'm also including a beta 2, which is, so it's the returns to education, but only for those coded as 1 in male. So like we did with just the binary indicator variable on its own, we can include a separate like additional piece for those coded as 1. So here, this beta 2 is capturing the additional returns to education for being male. So we have this, what we call an interaction effect. Education times male. So someone state the null hypothesis here. Yeah, Corin.
Beta 2 equals 0.
Beta 2 is equal to 0. if beta 2 were equal to 0, the slopes of these lines would be the same. But if they're different, we have beta 2 giving us the difference in the slopes. Okay, so this is how we can test for difference in returns to education by our binary indicator variable. Okay, so beta 1 is just the slope of education for those coded as 0, and then beta 2 is the additional returns to education. And then if you're just trying to get the returns to education for male, then you would add the two slopes. So beta 1 plus beta 2 would give you the diverging wage path. Okay, so this is how we code this up. So we have income, and then we have education as one of our variables, plus this, which is a interaction effect. It's essentially multiplying the two values together. So education times male. So we're gonna do this in code. I'm not gonna let you go just yet. We're actually gonna test this. So this is our third model, differential returns to education. And I want you to, like 30 seconds here, summarize what this is seeing. No compliments, no self-critique, just p-values and coefficients. Do we observe the presence of differential returns to education? 30 seconds, say something to your neighbor, and then we'll say it together. It's Pittsburgh, after all. Even Oakland, Mr. Rogers' neighborhood. Literally Mr. Rogers' neighborhood. Okay, is there the presence of differential returns to education by gender? How many of you are saying yes? Raise hands, please. How many of you are saying no? This should be of concern to the academy. We see differential returns to education. The p-value is not exactly 0. Hold on a second. I'm trying to get out of here. Let me just conclude. We see a very substantial p-value. We see an additional return to education if you're male, which is concerning. What we've done today is use real-world census records to test a important social question. Like we've done all this work to be able to build statistical models. This is an application some of you may be interested in. Some students in the past have done projects on these kinds of things. There are other ways of testing similar questions. And we're going to keep working with these kinds of models. I'm going to show you one more picture, and then I'm going to let you go. Or am I being rude? Another thing we could do is include not just differences in baseline income, the baseline gender wage gap, using differences in the vertical intercept, but we could also include differences in slope. And so this is a picture of how we can do both of those things at the same time. So different vertical intercepts and different slopes. So different returns to education and different baseline income levels. And this is the regression model that it spits out. We'll talk a little bit more about this next time. If you have more questions about this, feel free to stick around or come to office hours tomorrow. Hopefully you're feeling the power of this start to kick in now.